Welcome to the 21st class meeting of the Introduction to DSP. We are going to have our second quiz on this Thursday. It will come up to today's class meeting, and it's a close everything quiz, but you need to bring your digital equipment to upload your solutions to the PLMS. By the way, the problems will be given as a printed booklet. Okay, so we are covering chapter 8 and related chapters. So as I told you in the beginning of this course, the core knowledge you need to learn newly is the DFT. Actually, this up to this part, the topic is a kind of repetition of the material covered in the signals and systems. If your undergraduate signals systems was a very intensive course. Anyway, here goes some messages. So if you have time, briefly read and remind my messages and lessons. Here goes the review. So unlike our textbook where the DFT, the case DFT, case entry of the DFT output written as a summation or the product between the original entry of the vector and the W sub n, where W sub n is defined as e to the negative j 2 pi divided by n. We are not going to use this much, even though we are going to use, because I love this notation. And our textbook, which is very old, is, of course, old-fashioned. So let me tell you a story. When I became a graduate student in 1995, when none of you were existing, I could easily spot whether a paper, research paper, was published in Transactions on Communications or Transactions on Signal Processing, very easily. If I just flip the pages and see a lot of vector matrix multiplications, then it's definitely a paper published in Transactions on Signal Processing. And if it had a lot of integrations, then its paper appeared in TCOM, Transactions on Communications. However, amazing thing happened. While I was doing my graduate study, the trend changed. People now tried to rewrite almost everything as a vector matrix multiplication. So remember this. For example, suppose you have something like this. Then always see that, hey, this is a sum of product. A sum of products. Then just write it this way. Got it? Immediately. Then it gives you new interpretation. Sometimes it allows you to use some of your tools in the toolbox because now it becomes some area in linear algebra. So you may use, for example, eigenvalue, eigenvector, singular value decomposition, something like that. Got it? And another thing is like this. Suppose you have some, let me see. Yeah. Some of product, where one vector is scalar and the other is vector. Then what do? You immediately rewrite it as matrix vector multiplication, where H consists of capital H, these column vectors, and X consists of these scalar. This way, you can view summation of products in not only a very compact way, but also very easy way to understand. Got it? Anyway, So let's go back to our DFT. Even though our textbook and handouts love this notation. By the way, Professor Choi Jun-il, who wrote the most of the slides, our handout, try to follow the textbook. I think it's a very good way, because sometimes without presenting what is appearing in the textbook, but just show something else, confuses students a lot. In that way, this is a very good approach. However, I want you to remember this one. So this is nothing but that for what? For, of course, k0, 1, 2, dot, 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 up to n minus 1. So you have how many scalar equals scalar equalities? You have capital N equalities. So imagine you have n lines. Now you group these left-hand sides into a vector capital X underscore, and then this becomes that. Right? Of course, we can understand this Wn as a row of column vectors or a column of row vectors. Got it? So depending on how you view a matrix, sometimes you have what? You have the interpretation of the output, capital X, as a linear combination of the columns of capital Wn vector, or in this case, as an inner product of each row and the input, each row and input appearing in the output of the DFT. So in that way, DFT is nothing but bunch of inner products. So as you remember, these columns are what? A basis of the n-dimensional complex Euclidean space. Even though it's not unitary in the sense that it needs 1 over square root n to have normalization, but still you can interpret these as basis vectors of this C to the n, n-dimensional complex Euclidean space. And also, due to the fact that Wn Hermitian transpose equals Wn inverse n, remember, n. Okay, so yeah. So this relation, if you Hermitian transpose Wn, you have V0, V1, V2, up to Vn minus 1 in the columns, right? They are what? They are the columns of the inverse matrices. And they are also what? Also a basis of C to the n. So it's a really an orthogonal projection. Got it? So you need to have these two interpretations in your mind. By the way, especially at the end of last class meeting, we had something like this. Suppose a discrete time signal is periodic with period capital N, which is, by definition, x is the same as x evaluated at n plus n for all n. Then, if you find this DFT vector, then what's the relation between the Fourier coefficient CK and the DFT coefficient? And I told you that this CK is nothing but 1 over n xk. So directly performing DFT on your single period, then what do you have? You have the Fourier series coefficients, which needs to be scaled to be put here. By the way, our textbook has strange notation. and it's not standard, but says that Fourier coefficient is the same as DFT, but it depends on how you define a Fourier coefficient. Got it? Got it? Fourier series coefficient. Anyway, so you need to remember that. So far, it's exact. Given a periodic DT signal with period capital N, your one period DFT gives you what? Capital N times the Fourier coefficient of the periodic signal. Today, we are going to see something different, but it almost have the same interpretation, but never got confused. Anyway, so here we will focus on, and actually we talked about it in the last class meeting too, but anyway, we are going to consider finite duration or time limited discrete time signals. So here we have all zeros and all zeros except some finite duration. By the way, these ends, the collection of ends, is called a support of a function when we view the DT signal as a function. But in engineering textbooks or articles, mostly is said duration. So we have finite duration. Now, we take, so possibly non-zero part only from this signal with a lot of zeros. Got it? Of course, there are many ways to take them. As I told you, you may take exactly non-zero entries only, or you may include some preceding the interval or following the interval. And our textbook and I also emphasize that how we handle this so-called zero padding when we put something here or there. Got it? So these are padded or appended. Appended means usually that one, zeros. By the way, zero padding does not only mean we put some zeros after the duration, but we may put some zeros before the duration. Anyway, so here goes the finite length or finite duration DT signal of length n or length less than or equal to capital N. By the way, we are going to take n of them. Got it? And we have a vector. Temporarily, let's assume for convenience that we have taken from 0 to n minus 1. However, we may take from some n1, n sub 1 to n minus n sub 1 minus 1. So for example, suppose you have some y over n, and it's all zeros, and suddenly from n sub 1 up to n minus n1 minus 1, you have non-zeros and all zeros. By the way, how many samples do you have from n equals capital N sub 1 to n equals capital N minus capital N sub 1 minus 1? As you learned in high school math, if you have consecutive integers, what do you do? What do you do? You remember this way. 큰 수 빼기 작은 수 더하기 1. Right? So remember that. If it gives you confusion, just consider 1 from 10. Then you have 10 numbers. It's not 9 numbers. It's not 큰 수 10 minus 작은 수 1. You have to add 1. Got it? So bigger number minus smaller number plus 1. So in this way, you have y's. But as you see here, most of the textbooks just assume that we have taken from 0 to n minus 1. In that case, just consider this one. moving this to 0. Then this n1 becomes 0. Then this capital N minus n1 minus 1 becomes n minus 1, right? So let's define this as x of n, which is y of n plus n sub 1, right? As you learned in high school math, if your graph moves to the left side, you add by that number. Let's check. x0 equals y0 plus n1. Correct, right? So just assume this is the interval you've taken. Now, what you do is that, so you have xn, you take x underscore and perform periodic extension. By the way, what is periodic extension? How do you define? Actually, periodic extension is periodically extend or make a signal periodic this way. So you make copies countably infinite. So actually, periodic extension as an operation has a DT signal input and DT signal output. Of course, you can do the same thing for CT signal input, CT signal output. So here, x of n is an entire signal. Anyway, it's well, time limited in this case. So x tilde becomes a periodic signal with period capital N. By the way, how can you obtain the original signal from x tilde? You multiply a window function w defined as u of n minus u of n minus capital N. By the way, this u of n is unit step function, which takes value 0 or 1. And if the argument of the function is greater than or equal to 0, non-negative, then it becomes 1. So if you sketch this one, it has how many ones? Capital N ones from 0 to capital N minus 1. Got it? Anyway, so this way, you can get x of n back. By the way, be careful. We assume xn is time limited to this interval. That's why this holds. If x of n is not time limited, or if you take capital N of it, some non-zero values of x are discarded, then you can't say this. Got it? So be careful. It confused me a lot. Got it? Anyway, so basically this page, even though it uses modular or something, but anyway, exactly what I'm talking to you. Anyway, so now consider DFT of this periodic signal x tilde. And we know that this x capital X tilde k, the DFT output of x vector. So it's very confusing, but anyway. So this is periodic signal. So this is the Fourier coefficient. Got it? DTFS coefficient. Got it? So discrete time Fourier series coefficient is 1 over capital N, x tilde k, actually xk, but anyway, notation is really confusing. Anyway, yeah, so basically they are the same. Since it's really confusing. Yeah. Anyway, we already know this. By the way, using this W sub n notation, this is simply the definition of DFT. And this is what? This is the synthesis equation, right? This is analysis equation. And this can be shown that from this relation, the inverse DFT of X is same as this one. You can easily show this holds. Ready? So now, yeah, it's kind of repeating it again and again. That's why I covered this part last time and talking to you again. But anyway, let's see this figure. Seeing this figure is much informative. So you have original finite duration signal. So this is finite duration signal. By the way, what is the duration? Is it 4 or 5? 5, right? 큰 수 빼기 작은 수 더하기 1이에요. So here we choose capital N equals 5, but it's okay to choose any number greater than or equal to 5. Ready? Anyway, here we have chosen capital N equals 5, and we periodically extend this one with capital N equals 5. Then what do you have? We have all one signal because we have 5 ones. Now shift by 5. Shift by 5. Countably infinite. So we have all one signal. And we know from our signal gen systems or knowledge from DTFT, the DTFT of this signal is what? Is periodic impulse. Anyway, we can interpret this as periodic impulse with period 1. So so-called sampling function or comb, comb function has sampling function or comb function in the frequency domain. The difference is that if this period is 1, then that period is 2 pi over 1. That is 2 pi. Ready? So you have this, actually 5 here. And here goes the DFT. That is 5, 0, 0, 0, 0, 0. Ready? As I already told you, because it is same as you take 5 of them and perform DFT to have this. By the way, consider this one, right? Because this is X, right? And as you remember, this DFT matrix has all ones in the first row and first column. So if you multiply these two, you will have 5. And you know that these are orthogonal to that. So that is the result. Got it? So far, it's kind of review of what we learned. And here goes something different. So now, this example was so special. So let's consider a little bit a general one. Got it? So let's assume that you have a periodic signal x tilde, and you take, you window one period. So as I told you, by using Wn, which is rectangular window or rectangular function with duration 0 to capital n minus 1, duration capital N. So support 0, 1, 2, 3 up to capital N minus 1. So as you remember from signal gen systems, this is what? Multiplication in the time domain. Then usually, if you multiply some things in the time domain, what happens in the frequency domain? Convolution appears. The problem of discrete time signal is that your the frequency domain function is already periodic. So if you just convolve two periodic functions, then your integral blows up. So it's not the case, and you will find that the truth is that you perform single period convolution, which is actually called the periodic convolution. So in the time domain, you perform periodic convolution of two signals, which is the DTFT of this first vector and DTFT of the second vector. And we assume this window function a rectangular function. However, there are many possible window functions, not necessarily rectangular. There are many famous window functions: Hamming, Henning, Kaiser, some Chebyshev. There are many window functions. And they have found some good applications in some special cases. So you will see anyway later in this textbook. By the way, for the signal x tilde, original signal, anyway, we are going to say that we have DTFT x tilde e to the j omega, because we haven't specified what is the shape. However, for this window function, which is rectangular in this in our assumption, has very special DTFT. And this very special DTFT is related to so-called the Dirichlet kernel that appeared in the QE of this year. And I already told you and have given you as a homework problem already. By the way, in our homework and the Wikipedia, the Dirichlet kernel is defined with some odd number n, but it could be anything, any integer, for example, from 0 to n minus 1. In that case, its shape is a little bit different with possible delay, and this gives you the delay part. Usually, delay in the time domain appears as a linear phase shift in the frequency domain. So you have linear phase shift. By the way, why do we have this number? Actually, this is what? So we have from 0, from n minus 1. What is the center? The center actually is not an integer. However, it's summation of two endpoints divided by 2. That is this one. Ready? So exactly e to the negative j omega delay appears here. Ready? So if you have some fictitious signal that does not exist actually, then you have this one. Now this is delayed so that this location has become index 0. That's why you have this linear phase shift term factor appearing here in the DTFT. Got it? Anyway, once I told you already, the Dirichlet kernel, by the way, the term kernel is now too much used by computer science and engineering people as something else. But as an electrical engineer, kernel is, you may say it's a kind of function. Got it? Anyway, this Dirichlet kernel appears not only in our electrical engineering, but also in optics. Probably you remember something similar when you learned about diffraction in physics. You have grating lobes, something like that, probably at the end of the chapter. Anyway, so this appears again and again. Also, it appears when you learn phased array in modern array antenna systems. And array antennas are finds more and more applications these days, not only in military radar, but also in communications. So if you still do not know how to derive this one from the summation formula of a geometric sequence, then do your homework again. Got it? And just go to the Wikipedia and try to show this is the correct shape of in the frequency domain. Anyway, so what you need to do in the frequency domain is to periodic convolution with this one and that one. Got it? And this is shown here. Very confusing. But anyway, here the original signal. So this is original signal of finite support. X tilde is the periodic signal, right? Periodic extension. So, am I right? Yeah. So what you have is what? That integrated over a single period. Here, single period is chosen from negative pi to pi, but it's okay to be chosen to any 2 pi here. Okay. Then what you do is that the relation between x tilde and x is this one. By the way, it's very confusing, but this one is that one. Now you clearly see you have w e to the j omega minus theta. By the way, in these lines, from this line to that line is the most difficult part, but actually it's not. Your periodically extended signal is nothing but the convolution of these two signals, x and summation of delta of n minus kn. And we know that the DTFT of this periodic signal or sampling signal is periodic signal with period exactly the inverse of this period times 2 pi in the radian frequency. Got it? And you have this 2 pi over capital N. That's why from here to there you have this infinite sum. Now, even though you have infinite sum, fortunately we have finite integration interval. So among these infinitely many, see that our integration variable is theta. So among these infinitely many delta functions here, only capital N of them is involved here. But for simplicity, as I told you, this integration interval can be chosen to any 2 pi. So we have chosen 0 to 2 pi to make everything simple. So here we have lower limit 0 and upper limit capital N minus 1. Got it? Now, what is this one? Whenever you have direct delta integrated with some signal, what do you have? You have so-called the shifting property of the delta function. So integration becomes a scalar where this scalar is what? This factor evaluated at x equals a. So you have the same thing, capital X e to the j theta becomes x, capital X of e to the j, this one. And what is that one? This is the coefficient, DFT coefficient, case DFT coefficient. So you have that one. And here, this one becomes, the data becomes 2 pi k over n. So from here to there, you have the result. Now, what was the DTFT of the original window function W? Dirichlet kernel shifted by the center, right? So you have sine over sine appears here. And this is the delay part. So this one here by delay. And this one appears here by delay. Got it? So what does this mean? Your DTFT is, again, a finite sum of what? This function, Dirichlet kernel, shifted version of Dirichlet kernel, scaled by your DFT coefficient. Got it? So your original signal's DTFT is decomposed into n terms. And each term is what? The Dirichlet kernel. Properly shifted and linear phase multiplied. And here goes the coefficient. Got it? So let's see, where is the example? I've seen an example somewhere. Just a second. I cannot find. Probably I've seen from the textbook. Okay. Anyway. Yeah. So what I can tell you is this one. If we have finite duration signal, see that? Let me wrap up this part because it's very confusing. Okay. Suppose our signal is time limited. Our DT signal is time limited. And we want to find the DTFT of this signal. Got it? And what we do is that we take this part and perform DFT. And what we do is that we take our Dirichlet kernel, properly shifted in the K domain, or 2 pi k over capital N, and we multiply linear phase shift part and weight by the DFT coefficient, and we have perfect, this is very important, we have perfect DTFT back. See that? Here, this part is the most important part. If our signal was time limited, we can get the DTFT exactly as far as we want. Because anyway, this is function of omega, and omega ranges from minus infinity to plus infinity, even though it's periodic, right? So as far as we want to have higher and higher resolution, just evaluate this function, this Dirichlet kernel, as many points at as many points as we want. Got it? So this way, we've found an interesting method to find DTFT over discrete time signal by computing DFT of the signal, actually a part of the signal. But there is a very strong assumption that what? Our signal, original discrete time signal, is of finite duration. Otherwise, we have approximations, as we will see. For example, as I already told you in the first day of this DFT part, suppose we have some signal. We believe significant portion of the signal is here, even though there is some non-zero parts. Got it? And we want to do some frequency domain analysis, but we do not want to have this very large or possibly countably infinite length signal to be DTFT'd. right? Because we need countable infinite sum. So we truncate by multiplying a window function. Then original signal's some information is gone. However, we believe that the DFT of this part contains most of the important frequency domain information. Got it? Anyway, what is the most important is that some result is applicable when. This is very important. Otherwise, you will misuse our results and believing that you are doing something correct. But sometimes you see some abnormalities if you blindly use DFT. I also experienced that. I have taken some part of the signal and performed DFT. And there was very high frequency component, which is actually around at the center of the DFT output. But that was somewhat strange. Hey, this is acoustic signal sampled very fast, and I've taken some part. Why there is very high frequency component? And I traced back what I made mistakes. It was this. I assumed that from here to there, most of the important signal is there. It was almost correct, except that the signal actually started here. So the signal was moving that way, but I cut here. So what I have taken as a vector has what? Suddenly it's like 0, 0, 0, and some large value and smooth curve. In that case, this sudden rise, when I take the vector, gives me some strange high frequency component. So be careful. Actually, that is why people do not love this rectangular window. Sometimes they want to blindly just take some part of the signal from the DT signal and put a window. So usually what they do is that they somewhat de-emphasize this end so that you don't have strange high frequency component at your DFT output. Got it? Anyway, so here goes the properties of the DFT. And what you need to remember is that first, DFT is what? Linear transformation of a vector to the same length vector. So DFT is linear operator. And that is shown here, linearity. Okay. And also our textbook and slide says that it's different from DTFT. What is DTFT? DTFT has what? The entire signal in and this entire signal goes out. Got it? So they are different. They are closely related, as we've seen in some special cases. Anyway, so here goes the subtlety in zero padding. And the question is this one. What's the difference between the DFT of this part and the DFT of that one? So suppose you have a vector of length 5. Now you put 3 zeros of total length 8, and you perform DFT of this length 5 vector, and you perform DFT of this length 8 vector. Of course, here you multiply this 5-point DFT matrix, and here you multiply this 8-point DFT matrix. What would be the difference? Okay. Actually, you know they are different, right? You know they are different, and you should know what's the difference. Got it? Anyway. By the way, here it talks more about the circular shift part. So here goes the question. When you have this relation between underscore capital X and underscore X, what if you circular downshift? So it's in MATLAB, circ shift X some M. Is it M? Yeah, M. Means that you circular downshift this vector X. Got it? So circ shift X0 is vector X. So let me give you some example. 0, 1, 2. Circ shift X1 is what? 2, 0, 1. Because you downshift. The convention is downshift. Circ shift X -1. Then you have 1, 2, 0. Got it? Now the question is, let's define Y as the DFT of circ shift XM. Then what is the relation between X and Y? Got it? Or are they related, or are they arbitrary, almost arbitrarily related? What do you guess? So the textbook reminds us similar problem for a discrete time signal. So we have a discrete time signal X and DTFT capital X. In that case, if we delay by M, so graph is shifted by the right side of you, then your output, so let's say this is Y of N, then your capital Y of e to the j omega is simply what? Original signals DTFT times the linear phase vector. So the question is, so this is recall. Now, do we have something very similar in DFT? But in DFT, we cannot delay the signal, right? What if you just downshift this vector by 1 without circular downshift? You may have 0, 0, 1. Got it? So it's like this downshifted ones are out. We don't consider that one. Okay? We consider circular downshift like this. Got it? Actually, this is circular upshift by 1, but anyway. So the result is very simple. So let's say that x1, where is x1? Yeah. So yeah, it's confusing. So let's see. This is the definition. So x1 is what? 0. Is it downshift? Is it really downshift or upshift? X1 is X. It's very confusing. Just a second. No, is it really? Okay. Yeah. The textbook has. Okay. So, yeah, I'm sorry. So here, example shows kind of to us upshift because we have -2. So as you see that this one is shifted that way, got it? And circular shifted and appears here, got it? So notation is correct. So here this M is the amount of downshift as I've used here. Got it? So same notation. So you see here, if this part taken as vector x is circular downshifted by M, then you have this vector. Am I right? No, it's upshift. Upshift by 2. I'm sorry. Why the authors have -2 here? Anyway, so this is downshift by -1. Downshift by -2, which is upshift by 2. Got it? It's confusing. Anyway, and our results is here. So this is downshifted by M. So DFT of the vector downshifted by M. And amazingly, we have the same result. So here goes the original DFT, and here goes the linear phase shift part. So what we learned in continuous time Fourier transform and discrete time Fourier transform appears almost the same, except that we now have to have circular shift in order not to lose any information in the original vector. Because if we upshift the downshift without circular shift, some terms or entries of the original vector will disappear. In that case, we cannot or we may not directly relate the DFTs of the before circular downshift and after circular downshift. And it's kind of make very sense. Okay. By the way, here is some other properties, and I will cover this when I talk about fast Fourier transform algorithm, where we use these properties. But anyway, let's continue. So there is another one. We've already seen this. So multiplication in time domain becomes convolution in the frequency domain. We are going to see the same thing. The difference is that now we have two vectors, x1 and x2. And we assume they have the same length. So in our notation, we have these two vectors after DFT. Now the question is this one. The question is that given the two relation of four vectors, what is the DFT of x1 times x2? By the way, this is circ. Is it circ? No, it's O dot in LaTeX. O dot is called the Hadamard product. And it's very simple. You have entry by entry multiplication, not the inner product. So you still have length and vector. So we are asked actually, what is this question in terms of capital X1 and capital X2? Got it? And interestingly, we have this one. So let's say this as y. Then y equals 1 over n, and x1 vector circular convolved with x2 vector. By the way, you know the circular convolution of two continuous time signals of same period. And you know the circular convolution of, for example, two DTFTs, two DTFT of some signals. Now, here we have circular convolution. Here, n means length and circular convolution of two lengths and vectors. But anyway, so what is this one? this one is very similarly defined as our ordinary convolution. So let's see. What is y0? So we need to answer this question, right? What is the definition of this one? So what we do is that we circular downshift, for example, the right side, and consider inner product. So we have 1 over n sigma x1k x2k. Here, we need some mode something. Okay. 1. Yeah, something like this. So we circular downshift by 1. Yeah. Something like this. Got it? So you have this part. So let me rewrite like this. 1 over n x1 transpose circ shift x2 comma 0. This is 1 over n x1 transpose circ shift x2 1. Got it? So simply this inner product is interpreted as the inner product of two vectors. Got it? Yeah. And this is simple application, so you read it. Yeah, they are just examples. So let me just see. So in this case, just consider this way. Suppose you take these capital N terms and that capital N terms from signal x1 and x2, and let's call this as x1 vector. This is x2 vector. Now the question is, what is x1 circular convolve with x2? And as you see, the zeroth entry is just the inner producting these two. So you have, in this case, capital L, right? Just a second. Do we need divide by n? Yeah, just a second. Yeah. No, this is just the circular convolution. So we have L, got it? And if we circular shift this one, then what happens? This moves to the right, and you have 0 here. So you have L minus 1. And eventually you have zeros, something like that. And the value goes up again. Something like this. So you have something like this eventually. Why do we have something different here? Just a second. Now, I'm not sure why we have some different figure here. Okay, got it. Yeah, yeah. Okay, I found a mistake. I need to flip the signal. That part is missing. Okay, so how can I fix it? Yeah, this is not exact. I need to change this one. Just a second. I may need flip up down. Then circular downshift. Yeah, it's very confusing. So let me just retract my claim. Yeah, I forgot that one. So yeah, this part you do it. Got it? Something is wrong here. Got it? Yeah. So anyway, the result is correct as far as we properly define the circular convolution of two vectors. I forgot about flipping part. Anyway. Yeah, so this is also incorrect, and you must have that one. If L equals half of capital N. Anyway, let me emphasize again, you fill up this part using flip upside down and suck shift. Anyway, we are going to use MATLAB or MATLAB-like functions in, for example, Python. So you need how to use those functions to do circular convolution. Anyway, here goes the kind of one of the very important part of another application of DFT. So the question is like this. Just for simplicity, let's assume that you have two signals, X and H. For convenience, let's assume that these are both time limited. Otherwise, we have some different results. So we have taken this part and that part. Sorry. Can I just a second? Yeah, it's very confusing. Do I need to use L1 and L2? Just a second, let me see. Yeah, L and P. Okay, let me just, to be very general. Suppose you have some L1 minus 1 and L2 minus 2. L2 minus 1. Got it? So only here you have some non-zero, possibly non-zero. It may include some zeros, but anyway, some parts, discrete time. Now, the question is, compute the discrete time convolution or convolution sum of two signals, DT signals, and plot. By the way, what is the length, the maximum possible non-zero location here? You've seen in the homework already, right? And the simplest way to memorize is this one. Consider an extreme example where X is delta of N and H is also delta of N. Then what will happen? You convolve these two, then you have delta of N, right? So you have one non-zero component, one non-zero component, and one non-zero component, which is the sum of these two minus 1. So here you have sum of these two minus 1. So this one. Am I correct? Let me see. No, 0. Yeah. So in direct delta case, L1 is 1, L2 is 1. So you have, this should be 2. Got it? Right. So this one, got it? So whenever something is confusing, anyway, your answer is something minus something plus some constant, and you don't remember constant, then consider an extreme case. Then you have this one. So anyway, you want to fill up this part. You know these are all zeros. One of the way is that you take this vector as x of length L1, and this vector as h as length L2, and use MATLAB to convolve these two vectors. In MATLAB, the conv of x and h will give you the length, the summation of these two lengths minus one vector, as you see here. Got it? See that? This is L1 minus 1 plus L2 minus 1 minus 0 plus 1. No, sorry. Minus 1. Yeah, got it? Always confusing. Now, suppose your vector x and h is very long. Then this convolution is what? Each convolution involves a lot of terms, right? Because the discrete time convolution is defined as a summation, as you remember. Let's introduce the summation variable k. Then what do you have? If x and k has a lot of non-zero entries, then you have infinite sum. Fortunately, in our example, there are a lot of zeros, so you have finite sum. However, still, if this x vector and h vector is very, very long, then you have a lot of terms to be summed. Then, is there any way to circumvent this complexity? And a partial answer is to use DFT. Got it? So what we do is something like this. So let's say that this is n minus 1, for example. So we consider the n-point DFT where n is greater than or equal to this number. So what you do is that you take n of them, and you perform DFT, n DFT of this extended vector, n DFT of this extended vector, to get something related to the DFT of that vector. And what you do is that you inverse transform, you perform inverse DFT, and after some possible scaling, you put that vector here. Got it? That is the idea. And if n is chosen, for example, 2 to the sum power of n, integer, then our fast algorithms, such as FFT, outperforms in complexity than ordinary convolution. Even though we perform DFT on that, and inverse DFT on the possibly product, as you guess, product of the two DFTs. Because, as you see here, how many complex multiplications in general do you have? This is complex number, that is complex number, and you have up to capital N, or L1, L2, but anyway, that roughly capital N terms. And that N linearly increases, right? And for this one, you have another N. So N squared is the complexity. If you just perform blindly the convolution sum. However, as you will see, not today, because time is running up, the FFT has the complexity, asymptotic number of complex multiplications, big O of n log n. So this requires big O of n log n. That requires big O of n log n. Inverse FFT requires big O of n log n. And you know that when we have these things, we just drop that. So actually, ordinary convolution has quadratic complexity in the length, but we have n log n. Here, log n is what? Sublinear. So if n very large, we can save a lot of computational burden. Got it? Anyway, it's almost time's up, and we are going to cover this part from class meeting 22. Okay, that's all for today.